Everyone, my name is Sijia Zou. I am a postdoc at the Oceanographic Institution, and I work with Amy Bauer on the RAFOS floats of the OSNAP project. So today I'm going to talk about our work in progress with these RAFOS floats on the deep ocean circulation in the subpolar North Atlantic. Oops. Okay. So for those of you who don't know what a RAFOS float is, here's a quick introduction. The RAFOS is a range and fixing of sound, and as you can tell from the name, it's acoustically tracked. So in the photo on the left, I'm showing 4 of those floats to be released in July 2014. You can see each of them is about 2 meters long, and it's this.
Sijia, sorry, I don't see your slides changing.
Oh.
Yeah, I'm sorry to interrupt you.
No, that's okay.
I'm also not seeing them in full screen. I don't know.
It's so strange. Can you see the sharing now? Can you see the slide change now?
No, you're not sharing your screen.
Okay, I'm sorry about that.
I promise we tested before, right, guys?
Yeah.
Yeah, try putting the presentation mode.
Can you see it?
Yeah, now it's perfect. Yep.
Okay.
That's working.
Sorry about that. Okay, so the RAFOS floats. Photo on the left shows 4 of those floats, and on the right-hand side, I'm showing a schematic which displays the composition of the float. So basically, at the bottom, you can see that the float carries an acoustic hydrophone to listen to the sound signals. And also it is ballasted with a certain amount of steel weight, such that when the floats travel in water, they can stay on constant pressure level. And we have temperature and pressure sensors to measure these variables every day. And the maximum lifetime is about 2 years. So at the end of the mission, the float will release the weight and then go to the ocean surface to transmit the data. As part of the OSNAP, there are 125 RAFOS floats released in the boundary current along the rim of the subpolar region. So the floats were mostly released in the, all of them were released in the overflow water layer between 1800 and 2800 decibar. So in the picture on the left, you can see the spreading trajectories of the floats. So you see a pretty wide spread of those trajectories across the basin. In the picture on the right, I'm showing the launch locations of the floats along the OSNAP east line superimposed on the mean salinity field. So as you can tell from those black dots, which are the launch locations, all of the floats were released in the layer denser than 27.8, which is the overflow water layer. So the goal here is to use these RAFOS flows observations on the velocity field and to produce a graded velocity map. So for a more comprehensive understanding of the spreading pathways of the overflow waters on the large scale. So here's a more quantitative view of the number of float measurements. So here we have divided the domain into small grid boxes, which are about 1/4 degree in latitude and 1/2 degree in longitude. So which is approximately 60 kilometers of the size. So for most of the grids, we have float measurements exceeding 100 with an average of about 250. among all the grids. So there are certain locations where the measurements are sparse, such as in the northern Iceland basin right here, and also along the inshore rim of the subpolar region, in the interior of the Labrador, and also right here north of the Flemish Cap. So in this analysis, we only consider areas where the measurements are greater, the number of measurements is greater than 10. So here's the results. Here we use two methods, the weighted Gaussian interpolation and objective analysis. Both of these methods have been widely used on oceanographic and also meteorological data sets. And recent studies have also applied these methods on to produce graded velocity maps with surface drifter data and also Argo float data. So the results, mean velocity field based on the Gaussian interpolation is shown on the left, and the results based on OA is shown on the right. So here the white hatched area represents locations where the errors associated with the OA estimates are relatively large, such that those estimates may not be reliable. And if you remember the locations where we have relatively sparse measurements, these areas are basically where the measurements are few. So if we compare the two maps, we see a fairly well comparison between the two in terms of the flow pattern and also the magnitudes of the velocity. And the results based on the Gaussian interpolation are overall smoother compared to those based on the objective analysis. But the difference between the two is not significant for most of the grids. So here I'm going to focus on the map based on the Gaussian interpolation. And this is the same velocity field, but now I'm also showing the velocity vectors in black, which indicate the locations where velocity magnitudes are significantly different from 0. So here you can easily pick up the strong deep western boundary current around Greenland and also along the Labrador coast. There's also a relatively strong southward boundary current and along the eastern flank of the Reykjanes Ridge, and from about 59 degrees north to the Charlie-Gibbs fracture zone around here. And here you can see that the flow, the branch generally splits into weaker sub-branches. Also note that west of the Reykjanes Ridge, you see the mean flow field is pretty weak. So there's no concentrated boundary currents in this area. Other interesting features are that you can, in addition to the strong boundary currents, we also observe a number of recirculation cells and branches, and especially in the interior of the Labrador Sea and also in the Iceland Basin. So also northeast of the Flemish Cap, here the flow is much more complex. This is the location where the northwestern corner of the North Atlantic Current is located. So it's not so surprising that the flow is very complex. But also remember, this area is where the velocity measurements are sparse. So we need to keep that in mind when interpreting the results. So by subtracting this mean velocity field from the original float measurements, we can also deduce a EKE field. And again, left panel shows the EKE field based on the Gaussian interpolation, and the right is based on the objective analysis. So if you compare the two, you see the distribution and the magnitudes of the EKE compare pretty well between the two results. Superimposed on the maps are the OSNAP lines shown in red, and the colored circles along the OSNAP lines represent the EKE estimated with the daily velocity measurements from the moorings in the overflow water layer and below 1800 decibars. So we see a pretty good agreement between our EKE estimates based on the floats compared to the mooring-based EKE estimates. So there are a number of interesting features that we can see from these plots, but in the limit of time, I think here I'm only gonna look at this elevated EKE band east of Greenland right here. So you can see it extends from about 64 or 65 degree north and between this 2,000 and 3,000 meter isobath and onto the southern south of the Cape Farewell. So there are a number of disturbing processes that may contribute to this elevated EKE. And the first is about eddies. So here I'm showing trajectories of 50 RAFOS floats that traveled around Greenland. So if the float traced out a cyclonic rotation, then I put a red circle on that cyclonic rotation. So if it traced out an anticyclonic rotation, and then I put a blue circle. So basically you can see there are a number of cyclonic rotations observed by these RAFOS flow trajectories. And further analysis suggests that these cyclonic rotations are very likely to be associated with the Denmark Strait overflow cyclones, which were produced near the Denmark Strait and propagated southward in the boundary current to this area. Another attribution for the EKE field in this region might be associated with the variability of the recirculation branch. So here is a closer look at the mean velocity vectors around Greenland. So you can see that in adjacent to the deep western boundary current, there is a weaker recirculation branch which flows in the opposite direction. So it's northeastwards along this 3,000 meter isobath. And then at about 60 degree north, you see the branch crosses northward, crosses the 3,000 meter isobath and flows inshore. And you can see at northern locations, the recirculation branch rejoin the deep western boundary current. So previous studies, such as the one by Spa and Picard in 2003, have shown that this recirculation branch varies on synoptic and also seasonal timescales in response to surface wind stress curve. So this is another process that may contribute to this EKE field. Also, there are other noise or unknown variabilities which we have not thought too much about that may also contribute to the EKE field. Yeah, that's all I want to share today. And thanks for listening.
Thanks for the nice talk, Sijia. Any questions for Sijia? We have time for one or two quick questions. If you want to ask something, just unmute yourself and ask, or type it on the chat.
I have a question. It's Heather.
Yes, Heather.
Have you thought about a way to kind of estimate like how well you believe each grid point based on number of floats? You know, I can see in my mind the different trajectories, and I'm looking at some of the arrows and wondering if that's just one float making that mean, you know, in that one position. Have you started looking at that?
Yes and no. So for the Gaussian interpolation methods, we are also considering the degree of freedom to take that into consideration to estimate the standard errors associated with the mean in that method. Yeah. So in that case, we are gonna, yes, we are gonna think about the Lagrange integral timescales and use that to estimate the degree of freedom for the standard error estimates. But I don't think this is taken into consideration for the OA analysis. OA method.
Yeah, it's really interesting seeing the data like this, though. I really like it.
Any other questions for Sijia?
I have a question, Sijia. I apologize if I missed this, but I guess I'm wondering about variability in the flow with depth within the region you're considering. I guess you lump everything into one map. Are there any hints of, is that, does that feel like a reasonable thing to do to you? And I have no feel for how much variability there's likely to be across those different, once you get into the overflow waters.
Yeah, do you mean the different layers in the overflow water layer? different levels?
Yeah, absolutely. Mm.
Yeah, so we actually the big reason why we have to use all the data despite these pressure levels is that we don't have a lot of measurements to consider the vertical difference between these estimates. As you can, especially, we only have 125 RAFOS floats, and the some are released at 1800, some are released at 2800 decibar. And we actually tried, and I actually tried to, and you can see, I can show you this plot right here. So here you can see the blue lines represents the trajectories for floats between 1800 and 2400 decibar, whereas the purple lines represent the floats drifting at deeper pressure levels. So as you can already tell that there are much fewer floats available in the deep layer compared to the relatively upper layer. So that might be hard to do.
Yeah. Thanks, it's really nice.